Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to cover Pure Math 3, Complex Numbers Part 3, Modulus and Argument, which is basically talking about the trigonometric form and the exponential form of a complex number. So first I'm going to give you this formula. It's called Demovrous Theorem, and it's going to be up to you how much, if at all, you use it. In some of the examples that I have for you, we don't actually use this particular formula, but it is an extremely beneficial formula for you to be aware of, that it is at your disposal, and there might be certain times where you choose to use this method as opposed to a different method. So after we go through some of the questions at the end of the video, I might give you a short demonstration illustrating how this formula can be useful as you compare the different platforms. That is the algebraic platform versus a trigonometric platform versus an exponential platform. So I'll try to give an illustration, and whether or not you actually choose to use it in a particular Cambridge question will be up to you. So what we want to do now is just basically review and introduce this trigonometric aspect of complex numbers. Really, it's just like when you learn trigonometry in the beginning. You have your unit circle, and in your unit circle, you have this right triangle put. So instead of focusing on the Cartesian coordinate system where you have x and then y value to get to a particular point, so instead of having the x, y, now you're going to have the r theta. So another way of doing it is r theta, kind of like this. So there are two different ways of getting to the same location. One is with your Cartesian coordinate, where you go over on the x and up on the y. And then the other one is called polar coordinates. Polar coordinates have concentric circles. And so you start facing 0, you rotate a particular angle. And then when you're facing that angle, you go forwards a certain number of spaces. So how far you go is the r, and the theta is your angle of rotation from 0. And then you learn, because it's a right triangle, and you use your SOHCAHTOA, you know that sine is the opposite over the hypotenuse, and cosine is the adjacent over the hypotenuse. So your adjacent side is the x-axis, and so x equals r times cosine of theta, and your y-axis is r sine of theta. So what we do is when we introduce complex numbers, now it's instead of the x-axis and y-axis, it's the real axis and the imaginary axis. So your x-axis is the real axis, your y-axis is the imaginary axis, but it ends up working basically the same way. And we will use the designation r cis theta. Cis, again, is the abbreviation of r cosine theta plus r times I sine theta. Okay, so that's the abbreviation. So the I actually goes with the sine theta, and your r cosine theta is the real component. Okay, so what we're going to do here in the first example, let me take you to a question here. So you can see, it doesn't really say much. It just says, find the exact modulus and argument of u. So here's our modulus argument again. When you see those words, you want to think the trigonometric platform. And so we go back to our board here. And the u I've already written up here. It was actually from the previous part of the question. Our u is a negative root 3 plus I. And now we want to find the modulus and argument. In other words, we want to convert it from the algebraic platform, that is the a plus bi, and convert it into the trigonometric platform, the r cis theta. So remember, these are like sides of your triangle. So minus root 3 plus I, it's going to put you in the second quadrant. You do need to pay attention to the quadrant. The rest of it is quite easy, but for the angle, it is important to know what quadrant you're supposed to be in. So back on the x-axis, up on the y-axis, that's second quadrant. So I'll just write that right here so that we don't forget, second quadrant. Now to find the r is just the hypotenuse of this right triangle. So we can just use the Pythagorean theorem. So for for the r value, it's going to be the square root of negative root 3 squared plus 1 squared. It's an understood 1 on your I. And so you have negative root 3 and 1, and you square it and you end up with 3 plus 1, which is root 4, which comes out evenly as a 2. Then we also want to find the angle part. So to find the angle, which is the argument, the modulus is the magnitude or the distance that you go forward, that's 2. The argument part is the angle, it's the argument of the trig function, the angle. And so to find the angle, notice if we have the y and the x, we can use tangent from our Sekolah. Tangent is opposite over adjacent. So tangent of the angle is going to equal the opposite, which is 1 over the adjacent, negative root 3. So theta equals the inverse tangent of 1 over negative root 3. And when you solve this on your calculator, don't forget to be in radian mode. Radians is kind of the understood domain that we're working with complex numbers. And so our theta, when you do that in radians, comes out to a negative pi 6. Now, before we write this out, we need to check what quadrant we're in. Remember, we're in second quadrant. Tangent is negative in the second and fourth quadrant. Remember, all students take calculus. So all students take calculus. Tangent is positive in the first and third, negative in the second and fourth. So when we say a negative pi 6, that's going this way. From 0, it's going in the negative direction. That's a fourth quadrant angle. We want the pi 6 up here in the second quadrant. So we're going to take pi minus pi 6. So that's 6 pi 6 minus 1 pi 6. That's going to give us 5 pi 6. So our modulus argument form is going to be 2 cis 5 pi 6. So there we've converted a complex number that's in algebraic form, and we've put it into our modulus argument form. Okay, let me set up another question. Okay, for this next problem, we're actually working in the opposite direction. Says, of course, throughout this question, the use of a calculator is not permitted. So remember, you're supposed to be able to work with certain trigonometric features without using your calculator. A complex number with modulus 1 and argument pi thirds is denoted by W. Express W in the form of x plus IY, where x and y are real and exact. It's only 1 point, so you need to know what you're doing right away so that you don't take too long on this particular question type. And basically, they're giving you the modulus and argument. So you actually have 1 cis pi thirds. The modulus is the r, the argument is the angle. And they want us to convert it into basically algebra format. except it's using the vector notation instead of the a plus bi, but it's still in your algebraic format. And so all we have to do is actually just follow this through what it says. 1 cis pi thirds means that we do 1 cosine of pi thirds, and we do 1 sine of pi thirds. Now remember, pi thirds is 60 degrees. I think better in degrees than I do radians. So 180 divided by 3 is 60. We're not allowed to use our calculator. So we're going to pull up our special triangle here. Here's our 30, 60, 90 right triangle. And remember, your sides are 1, 2, and root 3. It's one of the 2 special triangles that you should have memorized. So if we're doing cosine of 60, that's adjacent over hypotenuse. So this equals 1/2. And if we do sine of 60, it's opposite over hypotenuse. That's root 3 over 2. We also want to pay attention to the quadrant. So pi thirds is in the first quadrant, meaning both of these are going to be positive because it's over and up. When it's in the first quadrant, 60 degrees is in the first quadrant. So now we can write this as W equals 1/2 plus root 3 over 2i. And there we have our complex number now written in the vector format instead of in the trigonometric format. So not too hard, pretty easy. Let's try something different. Okay, finally we get something a little bit more challenging than simply converting from one to the other. So let's take a look at this one. It says, again, not allowed to use your calculator. The complex number root 3 plus I is denoted by u. Express u in the form r e to the I theta. This is our exponential form. And of course, our domains between negative pi and pi. We talked about that in the first video. And then hence or otherwise, state the exact values of the modulus and argument of u to the 4th power. Notice the word hence. We're going to use that to our advantage. So I wrote here on the board our u in algebraic form. U equals root 3 plus I. And they want us to come up with the exponential form. And they also want us to find u to the 4th power, but it used the word hence. So first thing we're going to do is we're going to convert it to the trigonometric form first. So again, we need to find the r. The r equals the square root of root 3 squared plus 1 squared equals root 3 plus 1 equals root 4 equals 2. So there's our r. And we also need to find the theta. So the theta is going to be the inverse tangent. So I just went ahead and moved the tangent over. Inverse tangent of opposite over adjacent. So 1 over root 3. And we end up with pi 6 in radians. Again, since you're not allowed to use your calculator, you're going to want to use your special triangle, just like we did on the previous one. It's still except this time we're going the other way. So when you look at your special triangle, I guess I'll draw that again really quickly so that you can, here's 30, 60, 90, 1, 2, root 3. This is a 1 over root 3. 1 over root 3, where now we have 6. I think in the previous one we were dealing with pi thirds. This one is pi 6, but we have 1 over root 3. Opposite over adjacent is coming from this angle right here. Opposite is 1. Adjacent is root 3. That's this. So we know it's the 30 degrees. Convert your 30 degrees into radians. So 180 divided by 6 is 30. So you have pi 6 is this. Okay, so use your special triangles. You're not supposed to use your calculator. So now we end up with our trigonometric form, which is 2 cis pi 6. Okay, we're in the first quadrant, over and up, so we're okay on that, to the right and up. So that's first quadrant. So this is the trigonometric form. Now to move it into the exponential form is very easy because it already has r and theta in it. So all you have to do is rewrite it as 2e to the pi 6i. Okay. 2e to the theta I. I think Cambridge says I theta. It's multiplication order, doesn't matter up there. I like to put I at the end. So 2e to the pi 6i, where you see your r and your theta. So it converts very easily. You just need to know the form. So that's the first part of your answer right here is the exponential form. Then it says find the modulus and argument of u to the 4th power. You can actually do this several ways, and this is where we're going to actually choose to use Demovrous Theorem. You could go back and do the 4th power of root 3 plus I, but that would take a while to do. You'd have to do root 3 plus I times root 3 plus I plus root 3 plus I times root 3 plus I times another root 3 plus I. You'd have to have 4 of those, and it'd take a while to multiply all that out algebraically. This is where Demovrous Theorem is so wonderful, is when it comes to multiplication, it's so much easier to work in the trigonometric or exponential form. So you can do this actually one of two ways. We'll look at both of these. You can do the Demovrous Theorem, which deals with the trigonometric. So we're going to put this here to the 4th power, because this is our u. We already calculated our u, now in trigonometric form. Raise it to the 4th power. We're going to use Demovrous Theorem, and all that you need to do is take 2 to the 4th power. So 2 squared is 4, and another 2 squared is 4. 4 times 4 is 16. So we get 16 cis, and then you take 4 times the pi 6. So 4 pi over 6 reduces to 2 pi over 3. So here is the modulus, and here is the argument, the theta, the modulus and the argument. So that's one way of doing it, is doing it that way. The other way that you can do it is you can do it using exponential rules. So this time I'll put this in blue, raise it to the 4th power. Remember, exponents distribute to multiply, so you still get 2 to the 4th power, which is 16. E, and when you have an exponent raised to an exponent, you just multiply, and so you still get 2 pi thirds over I. So you get the same result. You still can see your modulus right here, and you can still see your angle right there, the argument, 2 root 3, 2 pi thirds. And it's just a matter of which platform you're going to work in. Again, the algebraic platform would take a long time because you have to manually multiply all those out. Or if you're really good with Pascal's triangle, you could try to do this with Pascal's triangle, but I wouldn't really recommend it because these other ways are so much easier to use. Demovrous Theorem is the trigonometric application, and then in the exponential, you're just following your exponent rules that you learned back in junior high school. So either way, you get your modulus, your argument, and you have your exponential form that they wanted you to end up in. Okay, let's look at another problem here. Okay, got an interesting question coming up here. here we have find the exact value of a for which the argument of the conjugate of u is equal to pi thirds. Remember, u asterisk or u star is the conjugate of u. So find the exact value of a for which the argument of the conjugate of u is equal to pi thirds. Now, we already solved part I in a previous video, so I have already put that on the board for us. So what we have here is actually the argument. In the previous part I, which we solved in one of the previous videos, either part 1 or part 2, we had u equals 6 over a squared plus 4 plus 3a over a squared plus 4. Now the conjugate, or the u asterisk, is 6 over a squared plus 4 minus 3a over a squared plus 4. And I forgot I. Okay, so that's our conjugate. And now what we need to do is find the value of a for which the argument of this is equal to pi thirds. So let's unpack that going backwards. What is the argument of u asterisk? Well, the argument would be your tan theta equals the opposite, that is the negative 3a over a squared plus 4 over the adjacent, opposite over adjacent, 6 over a squared plus 4. Of course, this is a complex fraction. It's going to invert and multiply. So the a squared plus 4 will end up on top and the 6 will end up on bottom. And you can see that the a squared plus 4 cancels out. You can also see that the negative 3 and 6 cancel. So what we get is tan theta equals negative a over 2. Negative a over 2. So tan theta equals a negative a over 2. And we want to solve for theta. So theta equals the inverse tangent of a negative a over 2. Now we want to solve for a given that the argument is pi thirds. So if the argument is pi thirds, then that is the angle. So pi thirds equals the inverse tangent of a negative a over 2. So now we're going to work backwards. Go this way. So tan of pi thirds equals a negative a over 2. Well, what is a tangent of pi thirds? So let's go back to our triangle. Maybe I should have drew it over here and just left it over here. So here's our 30, 60, 90. 1, 2, root 3. And we have pi thirds. Remember pi thirds, 180 divided by 3 is 60. So tangent is opposite over adjacent. It's just root 3 or root 3 over 1. So root 3 equals a negative a over 2. So when you solve for a equals a negative 2 root 3 is the value of a negative 2 root 3. Multiply by 2, divide by the negative, a equals a negative 2 root 3. That is our value of a in here, for which the argument of u is pi thirds. Okay, so again, focus on what argument means. So to find the argument, you use your tangent. Then once you find that, it's actually already giving you the answer. The answer is pi thirds. And then you've noticed that you've already reduced down to where you have a in a manageable, solvable situation where you can get a by itself. Okay. Now, I'll set up for one more. It won't be a Cambridge question, but it will be another illustration of how you can use Demovrous Theorem so that maybe gives you a idea. We already looked at it in the exponent with that fourth power, came in really handy. And I'd like to also show you one more application of it just in case you run into it. Okay, I just want to do a simple illustration to show you the flexibility of these platforms and how you can move from one to the other. And maybe it will help you understand also a little bit better how this Demovrous theorem can help you. Last time we looked at a fourth power, but what if we have a root, like a fractional power, like a square root or cube root? So I'll just run you through this simple illustration. Hopefully it will help you make some connections between the different platforms you're working with and also which tool will be more beneficial in which platform. So let's just take a simple concept like x cubed equals 8. Of course, we know that if we take the cube root of 8, we get 2. But actually there are 3 cube roots of 8. And we always think of 2 because it is the real cube root. There are 2 imaginary cube roots that are conjugate pairs. So how can we come up with those? Well, here's a little trick that you can use. These roots have to occur in our complex number field here, where we have our real and our imaginary. So if these 3 roots occur in this field, there's 360 degrees. So we can take 360 degrees divided by 3. That means there's 120 degrees between each root. We already know that 2 is right here on the real number line. And so 120 degrees would be over here. And we also know if you go 120 degrees more, it's going to be down here. So here you have 0. Here you have 120, here you have 240, and then you're back to 360. So there's 120 degrees between each of our roots, and our roots are length of 2. Now if we take these and make a right triangle with it, and you know that this is 180, 180 minus 20 gives us a 60 degree. And we know then that this is 30, and we have a 1, 2, root 3, and the same thing coming down here. We have 1, 2, and root 3. All we have to do now is put this into the proper quadrant. This one is second quadrant. So not only do we have 2, but x also equals a -1 because it's going backwards on the x-axis and up, plus root 3i, and -1 minus root 3i. There are your 3 roots of 8. X cubed equals 8 gives you 2, -1 plus root 3i, -1 minus root 3i. I won't show you the proof, but I'll let you try if you want to cube. Obviously, if you cube 2, you're going to get 8. You can also cube this -1 plus root 3i, multiply it out, and you'll be surprised that you will get 8. And you can take -1 minus root 3i and cube it. Remember, you need to do -1 minus root 3i times -1 minus root 3i times -1 minus root 3i. And again, you will get 8. I'll let you try that. What I want to show you is the flexibility of these other platforms. So in the algebraic platform, it was very easy to get the real value, but the imaginary values, we kind of had to work with it and think about it a little bit in order to get those. Well, what if we go into the trigonometric platform? So if we take this into the trigonometric platform, this would be 8 cis 0 degrees. X equal, or x cubed equals 8 cis 0. 8 on the real number line, and there's no BI. A plus BI, if you think of A plus BI, 8 is the A. There's no BI, there's no imaginary part, so you're facing the 0 degree because there's no imaginary part. So then if we cube root that, x equals 8 cis 0 degrees to the 1/3. Now we're talking about a fractional exponent, doing roots instead of exponents, and your formula still works the same way. So we end up with 8 to the 1/3 power. So x equals 2, 8 to the 1/3 power, cis 0 times 1/3 in times theta. 0 times 1/3 is 0. So the first root is at 2, 0. Notice that's exactly where we end up. Then all you have to do is add your 120 degrees. So you have 2 cis 120, and you also have 2 cis 240. And of course, if you use your calculator to convert that, doing 2 times cosine of the angle, you will get the x component. And if you take 2 times, for example, cosine of 120 is a -1/2. -1/2 times 2 is your -1. Okay, so if you take your 2 cosine of the angle, you'll get the a value. And if you take 2 times sine of the angle, you will get the y value, or the b value in a plus bi format. So this was very easy to come up with the 3. We didn't have to do this extra thinking. All we had to do was know how many degrees are between each root, and we were able to come up with it quite handily. What if we are in the exponent form? So let's take this down here and go over here. And we have x equals 8e to the 0i. Because we have 0 degrees, right? So here's our r, here's our theta. Well, what's 0 times I? Well, 0 times I is 0. And what is anything to the 0 power? 1. 1 times 8 is 8. So this we want to be x cubed equals 8e to the 0i. That matches our r cis theta, r e to the theta I, and it matches our 8, which is in the algebraic form up here. So algebraic, trigonometric, exponential. So e to the 0 is 1, 1 times 8 is 8. Now we want to cube root that. So x equals 8e to the 0i 1/3. Again, cube rooting it, showing fractional exponent instead of the radical. And again, you distribute it very similar to this. So you end up with x equals 2, 8 to the 1/3 power, 2e to the 0i. And then you end up with 2e to the 120i, and also 2e to the 240i. Now I use degrees. You can plug radians into those. Actually would be better. I just showed it to you in degrees because I think faster in degrees. Technically, you should put those in radians, but that's easy enough to do. The 0 is the same thing, whether it's 0 degrees or in 0 radians. So I showed it to you in degrees because the point is to show you the flexibility. If you are in the exponential platform, you're simply using exponent rules. If you are in the trigonometric platform, you're going to use Demovrous Theorem. And if you're in the algebraic platform, well, you kind of have to work things out manually. You can use Pascal's triangle if you are familiar with how to do that. Or you can use a little bit of geometry, trigonometry going on in here to try to figure it out. So that's how they all tie together. I hope that kind of helps you see some flexibility that you have depending on the Cambridge question that you get. What's important is all of your prerequisite skills are at your disposal, and you want to use those. All you're doing is then applying it to complex numbers. I hope that helps. And thank you for joining me. Hope to see you again next time for part 4, where we look at the graphing part of complex numbers on the Argand diagram. Thanks again, and see you next time.